Okay, so let's see this picture. Oh, that's not cool. The way they hooked that pulley up. What is the kinetic energy of K when we release the system and L hits the ground? Okay. Yeah, this problem is definitely more complicated than the last one, Dodo. But we've got 30 again, so that's nice. There's a pulley here, a floating pulley here, a ceiling brace here, and then a rope that goes like this. And then on this is what we're calling L. It has a mass of 2m, and it is a height h above the floor. And then there's a block here which has a mass m. Do we want the kinetic energy of the system or the kinetic energy of just one of the blocks? And am I assuming in the picture? Oh man, this picture is annoying. Am I assuming that these are the same height whenever I draw this? Am I assuming that's true? And I guess I'm solving it in terms of h again. Or this is some height h. Okay, so let's look at the potential energy initial of the system. We're going to get 2mgh plus, and then how high up is m here? Do we know how high up m is? You know what? It won't matter. I'm gonna do something dastardly. I am going to set so we don't know where that mass is. No, you want the sign of it. Dodo's right. When this falls, it's going to be 2mgh. That's what its changes here. This, when it goes up, this is going to move up this way, 2h. And you want the sine component of that. And since you know that's 30 here, sine of 30 is going to be half, so this is essentially moving h here, which means this change here is just going to be mgh. Which leaves you with an mgh extra of the kinetic energy. But if the answer is just mgh, you would have already answered it based on what you have here. Why do you have mgh over 3? Or am I looking for just one of the masses? Am I looking for just mass L or mass K? Or am I looking for the whole thing? Buna, Glor, System, Serbest, I don't know what that is. Am I looking for the system or just this mass kinetic energy or this mass kinetic energy? It asks K's kinetic energy. Okay, so I'm looking for this one's kinetic energy. Okay. So give me a second, let me think. No, you don't want to do the tension. I have a gut feeling My gut is telling me it's 2/3. I don't know why my gut is telling me that. And I haven't worked out any of this because I'm still thinking through it. My gut is telling me the 2/3 solution. Why is it telling me that? Is it telling me this because this is moving faster? Yeah, my gut is telling me 2/3. Let me see if I can work out the math. Why is my gut telling me that? That's what my gut's telling me. This is the weird thing of physics. Like, you know, you've done a lot of physics when your gut has the right answer and you cannot formulate why that is the answer in your mind. It has to do with the velocity, though. Kinetic energy is 1/2 mv squared. I wonder if I could do this. Okay, so let's check this out. The total, will that work? Okay, let's just try this out. I don't know if this will work, but I'm going to do it, and we're going to see what the heck happens. The total kinetic energy I have in my system after the end of this is the mgh I have left over, which is what you had on the paper for your, what you have written as EK, but it's really the energy of the system. So the total kinetic energy I have in the end is mgh. Now this has to equal the kinetic energy of block K and the kinetic energy of block L. The kinetic energy of block K is 1/2 m, and then I'm going to just leave this quantity squared blank for a second, and this is going to be 1/2 of 2m and then some quantity squared, just for a second, okay? If this block L is falling a distance h, that's how far it's moving, it is doing that distance here, h, in the same amount of time that the other block is covering 2h worth of distance. Because of this, I know block K is moving twice as fast as block L. So I am going to say that this is like 2 velocity, and this is 1 velocity, okay? Did that do what I wanted it to do? I told you I didn't know if this was going to do what I wanted it to do, but because this is going to give me a 4/2. Yeah. Yes. Yes, I did it. Here's how you do it. Figured it out. Okay. So this is why this works. So the hanging block, the L block, it's falling just a distance h, and it covers that in some amount of time. The other block has to be moving twice as fast to cover twice the amount of distance in that amount of time. So the first thing I can do here, if I just want to like clear up this math, is I'm going to get rid of the m's because who cares? And we can just put the m's back later. It'll just show us this math a little bit easier. What I see here is I'm going to get 2v squared, which is 4v squared over 2, plus, and then on this side, I'm going to get 2 times v squared over 2. And if I throw the m's back in, here's an m, here's an m, here's an m, I'm going to get the mgh, okay? What this means in total is that this 4/2 is a value of 2, 2/2 is a value of 1. So what I get for my total quantities here is that this is 2 kinetics and this is 1 kinetic, and that has to equal the total value I have, 3. This means that block K has 2 of the 3 kinetic energies, as we can think about that. So before, when we did the previous problem, we were able to just divide by the mass here, because all of the masses were moving at the same speed because the angular velocity was the same because they were all attached rigidly to the rod. In this case, because they're moving at different speeds, each one has its own independent kinetic energy in terms of that. The kinetic energies, those velocities are different. And since that velocity value is squared, it means a lot more. So in doing that, knowing that there's 2 for this first block K, and then 1 for the second one, we can set up this kind of ratio and see this is 2, this is 1. That means the K block is going to be 2/3, 2 of the 3. And that's what my gut was telling me. My gut was telling me all this math here, and then we just had to go find the way to victory. Okay? Yeah, as you do like a lot more of those type of problems, your gut is always the number one thing to listen to. And it's a tough thing to listen to it because, sometimes you just want to divide it by the mass because it looks like a different problem, and then, you get the 3 instead of the 2/3. I'd say that the hardest part of this, which you got immediately, was that because this is a pulley system, that this block is going to move twice as far. That's something that if students think that they're both going to move the same, then they would just divide this by 2 and get B as the answer instead. So you did a really good job of immediately recognizing, based off of the one floating pulley, the mechanical advantage of the system and seeing how much further that block is going to go. So thanks for noticing that, because that's something I haven't done pulleys like this in a while. And if you don't have that information, you can't do this problem. So definitely good job there. And yeah, there's a lot of Dad, you're right. There's a ton of abstract fundamentals there. There's conservation of energy. There's understanding pulleys and seeing how the distances are different. There's understanding how you can put in dummy values for problems to get ratios and how the velocities need to be squared. You need to understand that pulley system is frictionless and the rope won't stretch, so that's like a rigid system, so that they can, fall at those speeds like that. There's just a lot going on in that problem. Yeah. The 2/3 gut feeling. Always trust your gut. So, definitely trust your gut. Oh yeah, and it's definitely a great exam question. It's a great exam question if you're only giving a few problems and you want them to be harder problems. You know what question? This question is in the easy part of the book. I'm wondering about the hard ones. The hard ones are probably very similar to this, just with maybe more pulleys. Because it's not a it's certainly not a question you can look at and immediately get the answer. The only way you're immediately getting the answer of this is if you do these problems. And the reason why professors and teachers, we assign problems to do and just kind of grind through is because, if you don't have that physics gut feeling, if you weren't born with that for some magical reason, then the only way to build it is to do a bunch of these. And, once you build that gut feeling, you've got a pretty good idea of what some of the little tips and tricks and little moves that you can do in the world of physics to get these answers pretty swiftly. In which case, then it is an easy problem. But, yeah, for the students who have never looked at these problems before and have just kind of, opened the book as you're seeing the problem for the first time, they're hard the first time you do it. But as you do a few more of them like this, it definitely, gets a little bit faster. Yeah, definitely for energy questions. Dodo, is this a high school or a university class, like a college? Are you prepping just for a midterm or a final exam, or are you prepping for an AP question? High school. So are you prepping for the AP exam? Oh, and dad, like, so what we call that's called a floating pulley right here. And it, yeah, I kind of drew it poorly. The way it's drawn in Dodo's picture, there's like a ceiling here, and then the rope comes down and then around, and then it hits this pulley, and this is actually where the block's like that, and then this goes down and there's a block over here. That's how it looks. I drew it poorly because I'm a terrible drawer. Turkish AP exam. Is that like the College Board one? Because I know they give an international version of it.